Assalamualaikum. My name is Noha Fiza binti Ali. Matric number CE190089, and this is the filler table of this project. I will present the filler table. As we can see, we have 6 facts, and what ideas that we have get from the facts, and then the learning issue is first how to analyze the PCM. Hence, we use the MATLAB or Simulink software to analyze the output of the PCM and use oscilloscope to display in MATLAB or Simulink, which is to display the waveform of the PCM output. And then the second is what is the device that can code and sample analog device. Hence, we know that we have to use sample and hold. And then what is the device to convert the quantitative signal to binary codes. Hence, the action that we do is we use encoder. And then what is the device to convert the value for continuous amplitude sample to discrete time signal. And then we know that we have to use integer to bit converter. And then what is the device to decode the pulse coded waveform. And then we know that we have to use decoder. And lastly, what is the device that can eliminate high frequency components of the message signal. Then we know that we have to use low pass filter. That's all from me. Thank you.
Assalamualaikum and good day. My name is Nur Dania Meji Azama with matric number AE190066. Today I will present my part, which is my map. Firstly, there are 4 important points from the pulse code modulation, or known as PCM. Firstly, the basic properties of PCM is sampling rate, which is number of times per second that samples are taken. Next, the basic properties is bit depth, which is determines the number of possible digital values that can be used to represent each sample. Next, the basic element of PCM. There are 7 basic elements of PCM, which is low pass filter, sampler, quantizer, encoder, regenerative repeater, reconstruction filter, and lastly decoder. Next, the advantage of PCM is pulse code modulation is used in long-distance communication. Next, the efficiency of the transmitter in PCM is high. Thirdly, the higher noise immunity is seen. And lastly, efficient method. And the disadvantage of PCM is the bandwidth requirement is high, and the PCM is a complex process since it involves encoding, decoding, and quantization of the circuit. That's all for me. Thank you.
Greetings to Doctor. My name is Shankar Nalaki Subramanian, matrix ID AE190090. So I'll be explaining about part A. The circuit has been simulated in reference to the diagram given in the question. A pulse generator has been set at an amplitude of 5 with a period of 2 times 100, 1 over the equation. This is because according to the Nyquist equation, it needs to be 2 times. So this is in seconds. And the sampling with the duty cycle of 50%. And the frequency has been given from the equation is 2 pi 100 radian per second and 5 amplitude. So this is a sample and hold block. This is a uniform encoder. The bits has been set to 5 peak and 4 bits. The integer to bit converter has been set to 4 peak. The bit to integer converter has been set to 4 peak. This is a uniform decoder, 5 peak, 4 bits. And this is a sample and hold. And this is an analog filter, Butterworth type. So that's a demux right here. So if we run the simulation, this is the output waveform. As you can see here, we have a uniform sine wave here, but the output here is not as consistent because this is actually the minimum required. As we increase the value, it gets more uniform. And this is the bits. So that's all for 4 bits. Now let's talk about 8 bits. It's the same circuit, but now the peak has been set to 5 peak and 8 bits. And here also has been set to 8 bits. Here has been set to 8 bits, and also the uniform decoder has been set to 8 bits. The peak has not been changed, and this has been, I just added a few more lines for the PCM. So let's run the simulation. So let's look at the output waveform. So this is a pure sine wave, and this is a output. It's not that consistent. And this is the waveform for the PCM bit encoder. the PCM bit scope. So this is it. So that's all from me. Thank you.
My name is Brandon Dennis Chamachu, matrix number 8E190103. I will be explaining part B for scenario 3 and scenario 4. For scenario 3 and 4, they have the same sampling frequency, which is more than 200 FM. Here we are using more than 2 FM. Here we are using 200 FM, which is 200 times 100 Hz. So we get 20,000 Hz. And for scenario 3, we are using 8 bits of encoded PCM data, while scenario 4, we are using 8 bits of encoded PCM data. So this is the simulation. This is the output we run. So this is the output graph of the top one is the input, while the bottom is the output. So we can see the output of the graph, we have an initial delay before reaching a stable oscillation, while the amplitude for the input is 5, but the output is, the amplitude only has around 3.16. The amplitude is 3.16. Well, then this is the encoded PCM data for 4 bits. And this is the process of decoding the process of decoding. So the top is the top graph is the output of the bit to integer converter. The bottom is the second one is the output of the uniform decoder, and the third one is the output of the sample and hold. And this is the encoding the process of the encoder. So the top one is the input. We have 5 amplitude. Then the second one is after the sample and hold. The third one is after the uniform encoder. Now we simulate for 8 bits. Here we change to 8. And we need 8 outputs, sorry. Let me run. So the top is the top graph is the input, while the bottom is the output, and we still have an initial delay, but the amplitude of the output compared to the 4 bits, the amplitude of the 8 bits is higher at 3.5, around 3.515. So this is the 8 bits. You can see all the bits. This is the encoded digital signal, while this one is the decoding process, and this is the encoding process.
Next, I will present the simulation for part C, where the condition is sampling for empties is lower than minimum required according to the nucleus. The scenario is sampling frequency is less than 2 FM and the n bits encoded PCM data is 4. Hence, from the calculation, we know that we have to change the sampling frequency to 0.2 FM and the n bits encoded data PCM is 4. This is the block diagram, and we have to change the period at the push generator here, and then OK, and then we click run to run the simulation, and then to see the output waveform. Here is the output waveform. We can see that compared to other scenarios, the waveform here is very fuzzy, where the amplitude is not consistent because of the aliasing phenomenon. As we can see here, this is the waveform that have been zoomed. The upper here is the input waveform, while the bottom here is the output waveform. The sampling frequency is too low, thus the signal separation also decreases, and we can conclude that from the waveform that the original signal cannot be recovered from the sample signal. And to see the graph for encoding and decoding process for scenario 5, we click this curve, and as we can see, this is the result for the graph for encoded digital signal for 4 bits, and the sampling frequency is set to 2 Hz. That's all from me. Thank you.
So for part D, we are changing the amplitude from 5 to 15. It's 15 and this one 15. This is for 4 bits. So we can see the amplitude of the output graph increases, but is not the same as the input. It increases to around 9.5, and we can see the frequency is the same as the input. Should be 100 Hz, around 100 Hz. So this is the decoding process. And this is the encoding process. You can see all the amplitude increases to 15, except the output of the uniform encoder. And this is the encoded digital signal for 4 bits. So for 8 bits, we are changing this one to 8. And we need the output. So for 8 bits, we can see the frequency is still the same as the input, while there is still an initial delay. There is still an initial delay at the output, but the amplitude is higher compared to the 4 bits, for 8 bits. Just now it's 9.5, now we get around 10.545. This is the 8 bits in digital encoded signal, and this is the decoding process. Well, this is the encoding process. So for the second part of part D, we are changing the amplitude to 0.5. So this is for the 8 bits. So here we can see the graph of the input on the top and the output on the bottom. The frequency still remains the same, but there is still an initial delay, but the amplitude changes. So the original amplitude is 0.5, but the output is around 0.3515 for 8 bits, and this is the encoded digital signal for 8 bits. Here we can see the signal, and this is the decoding process. Well, this is the encoding process. So now we need to see for the 4 bits for amplitude 0.5. Okay. So we change the bits to 4. So for an amplitude of 0.5 and sampling frequency of 20,000 Hz, and PCM data is 4 bits. This is the output on the bottom and the input on the top. The frequency remains the same. There is an initial delay, but the amplitude of the output is lower than the 8 bits and more inconsistent. The average is around 0.3176, while the 8 bits has more consistent amplitude or oscillations, and the amplitude is higher than for the 4 bits encoded PCM. So this is for the 4 bits, the encoded digital signal. This is the decoding process of the 4 bits. You can see the waveform is a modified sine wave, and this is the encoding process. That's all from me. Thank you.
Hello everyone, my name is Shivara Anaki Murugan. My matrix card number is AE190089. Today I'm going to explain all about how to make sure the resultant recovered signal is same to the modulating signal. So in our case for part D, I'm taking the 0.5 voltage peak. So for our case, when the voltage peak is set to 0.5 volt and the resultant output waveform recovered signal will get somewhere around 0.3 volt, which is not insignificant and desired by the current simulation. So to enhance this issue, so I'm gonna add one additional block, which is the gain. The function of the gain is to amplify the signal. So in our case, I set the gain value to 1.5, where we can amplify the modulating signal by 1.5 times. So initially we will be getting around 0.3 voltage. So once we amplify it by 1.5, we will get somewhere around 0.45 volt. So which is the closest and similar to the modulating signal, which is the peak of 0.5 volt. So now once we done it, we can run the program, and we can observe that both the input for the modulating signal and the recovered resultant signal, the waveform is achieving almost to the peak of 0.5 volt. So once the simulation is done, this is the modulating signal waveform. So once we zoom it, we can see a purely sinusoidal with a peak of 0.5 for the modulating signal. And now this is for the recovered resultant signal. So we again zoom it, and for this case also we can see that we will achieve almost a 0.5 voltage. So for the recovered signal, so overall, to be concluded, to improve this method, we can use one additional block, which is the gain element, to make sure the both modulating signal is similar to the resulted recovered signal. So that's all from me. Thank you.